Hello everyone. Today we'll understand about quantum mechanics. So this quantum mechanics is somewhat different from the classical physics or classical mechanics in the sense that it deals with the particles at a microscopic level, and it cannot tell about the exact position, momentum, energy or time of a particular particle. Rather, it tells or it gives the probabilistic nature of a particle, and we cannot say that it is the shortcoming of that particular approach. Rather, it is the strength of this approach. So this quantum mechanics is basically is dependent on Heisenberg uncertainty principle and the Schrodinger wave equation, where Heisenberg uncertainty principle utilizes the mathematics of the matrix and is called as matrix mechanics, and Schrodinger wave equation, it utilizes wave equation and therefore called as wave mechanics. However, the basic principle of both the approaches are same. So we'll start with the Heisenberg uncertainty principle. Now, as I told you, this quantum mechanics deals with the particles at a microscopic level. So this Heisenberg uncertainty principle is for microscopic level, that is the particles that are very, very small. Let's take an example of an electron. So what is this? As per this principle, we cannot find the exact position of a particle. Rather, we can tell the probability of finding the particle at that particular position. So what is it? As per this principle, it is impossible to describe with absolute precision about the position, momentum and energy of a particle, such as electron. So instead we can tell the average value in the sense like expectation, because in probability we used to calculate expectation. So this is that expectation. So what is this uncertainty? This uncertainty is not a shortcoming of this quantum calculation, rather it is a strength that describes the probabilistic nature of events that involves atoms or electrons. This is what I told you. This is not a shortcoming of this quantum mechanics approach. So what is this Heisenberg uncertainty principle? Heisenberg said that it is very difficult to tell the exact position or momentum of a particle simultaneously. Like the magnitude of this inherent uncertainty is described by the Heisenberg uncertainty principle. We cannot tell that what is the exact position, where x represent position and p represent momentum. So what is this principle? Delta x into delta p must be greater than or equal to h cut, where h cut is nothing but h upon 2 pi. Similarly, uncertainty in the energy and time can also be calculated. What it is? Uncertainty in the energy measurement will be related to the uncertainty in time at which measurement is made. So delta E into delta T must be greater than or equal to h cut, where h is nothing but Planck's constant, which is very, very small number. So what is the overall implication of this uncertainty principle? Implication is that we cannot properly speak of the position of an electron. Rather, we can tell about the probability of finding an electron at a certain position. How it is? Like this is the implication. Let us suppose this is when electron is behaving as a wave, because it is of dual nature, particle nature as well as wave nature. Let us suppose it is behaving as a wave. So this is the wave that randomly this is the probability of finding the electron at this particular position is very, very high. Probability of finding the electron at this position is very, very low. We cannot tell that electron is exactly at this position or this position. This is the electron that we have made. We cannot tell that electron is exactly at this position, but what we can tell that the electron will be somewhere between this to this particular position. So instead of telling the exact position, we can tell where it is. So whenever we are dealing with the probability, we'll deal with the average or expected values. So what we will do, we will do the probability. We will take the probability of this particular area, and then we will integrate between these two limits. This is in the lower limit and this is in the higher limit, and that can give us the overall position. That can give us the average position of the electron within that particular area. So the important result of this quantum mechanics is the probability density function, PDF, that can be obtained for a particle in a certain environment and can be used to find the expectation value of important quantities like position, momentum, energy, that along with the time. So mathematically we will understand it how it is. Let us suppose we toss a coin. Whenever we are tossing a coin, so probability of appearing head or probability of appearing tail is always 1 by 2, because total probability is head and tail 2, and getting head is 1 and getting tail is 1. So that's why what is the outcome divided by total, so 1 by 2. Same in the case of the deck of cards. Let us suppose we have 52 cards we are playing, so drawing a particular card out of 52 card is 1 by 52. So now, in the same manner, we will understand this probability. Let us suppose probability of finding the electron in a particular range is px, where x is nothing but that range it is representing. So px is a probability density function for a one-dimensional problem. One-dimensional, like we are dealing only with the along the x-axis. We are not at the moment dealing with y and z as well. So what is the probability of finding the particle in a range? That is minus infinite to infinite px dx. Okay, and if we are doing normalization in the sense like overall probability is 1, so this is equal to 1. If we are not dealing with the normalization, then we can take it separately. So what this overall expression indicates, it implies that the particle will be somewhere within this particular range. This I told you here, that particle will be somewhere in this range, but we cannot tell particle is exactly here or here. We can only tell about the probability of particle within this particular range. So this is the probability density function that we will be able to find out with the help of this uncertainty principle. Now what is the average value? Because after utilizing the probability function, we need to calculate the expected value. So the expected value or the average value, what we will do, we need to multiply the value of that function in each increment dx by the probability of the finding the particle in dx and sum r over x. So what is the average value? This is average value is always represented by like this. So average value of the fx is the range in which we are trying to find the probability, minus infinity to infinity, or say x to x plus dx, or whatever it is. Say let us suppose we want to find the range of the particle in between 1 to 2, or say 3 to 7, whatever it is. So whatever be the range, we will utilize it. Minus infinity to infinity indicates that our numbers would lie in this particular range. The fx is the function increment in that particular area, and then px is the probability. This is the average value. Mind it, this is the average value in case when we are when our function is already normalized. But when the PDF function is not normalized, then the average value would be this value divided by the overall probability, overall PDF in that particular range. So this is all about your Heisenberg uncertainty principle, wherein we would not be able to tell the exact position or momentum of a particle simultaneously. Same, we cannot tell exact energy or time of a particle simultaneously, but we can tell the probabilistic nature of the particle in that particular range. So just go through it. If you have any doubt, drop a message. Thank you.